Hello, everyone. Welcome back. This is Monica Lupion, and I'm going to continue with the analysis and discussion of heat transfer and the fundamentals of heat transfer. We covered already heat conduction and a brief introduction about heat transfer. And now in today's video, I'm going to focus on heat convection and also how we can use the similarities with the electrical circuit to study heat transfer. So let's begin by defining heat convection. And in this case, we're going to use the Newton's law of cooling. That's the expression and that's the equation that govern the convection situation. So what we have here is that if you remember from the introduction, in the case of convection, we need source of heat. Of course, it has to be a gradient delta T between the source and the receptor. But we also need to have some. Let me put the pointer. Some moving fluid. So this is the important an important aspect that is different from conduction. So we need to have a moving fluid in order for convection to happen. So what's the general equation for convection? Well, we have that the heat transfer is equal to the convective heat transfer coefficient times the area times delta T. So if you remember from the previous video when we studied conduction, we defined conduction as a function of the thermoconductivity, the area, and dt dx. Okay, so you see the similarities between these two expressions here, and also the role of the convective heat transfer coefficient H compared to the role of the thermoconductivity K. And I mentioned that the thermoconductivity K was pretty much depend on the type of material and the temperature. For the case of the convective heat transfer coefficient H, well, this is a more sophisticated coefficient, and it depends not only on the type of material and the type of the temperature level, but many other things that we also need to consider. So it's not as easy, let's say, as the determination of the coefficient K. It's more sophisticated, and we're going to spend a lot different lectures trying to define or calculate the value of this convective heat transfer coefficient H. Okay, what else we have? We have the area, and we also have the temperature difference. So we still need delta T in order for the heat transfer to happen. Different values of the convective heat transfer coefficient. Well, depending on the type of mechanism, if you remember when we discussed the introduction of the three main mechanisms, I mentioned that in the case of convection, we have free or natural convection, or we have a forced convection. Of course, the aim of this first convection is to promote heat transfer. That means that the heat transfer coefficient is higher in the case of forced convection compared to natural convection. If we have a higher convective coefficient, we will have a higher heat transfer rate. Okay, if we compare liquids and gases, usually liquid systems would typically have higher H values than gas because of the higher density. Okay. Also, when there is a phase change, for example, if there is some boiling water or condensing vapor, the value of the convective H coefficient will rise quite a lot, as you can see here in this table. When we compare boiling water, condensing vapor to any natural convection, that is, when there is a phase change, we are promoting the values of H, and we will have high rate of heat transfer. Okay, so let me now move to the case of these similarities between heat transfer and electrical circuits. Okay, so if you remember when we study or when you study Ohm's law and how to solve electrical circuits, one of the main or the basics that you study is the case of having a circuit in series. This would be the case, okay, in parallel, right? Or when you have a combination parallel and series, like in this case. And the strategy to solve this kind of situation is to find the value of the resistance R. And then, well, if we have the Ohm's law, you can divide the voltage by the resistance, and that has to be the same as the intensity. In the case of heat transfer, we're going to use a similarity. Heat transfer will play the role of intensity. Delta T will play the role of voltage, and the thermal resistance will play the role of the electrical resistance in a circuit. So first, what we need to do is to identify if we have a circuit in series or in parallel. And here, as you can see, we have three different elements, one after another, like this. If we use the analogy with electrical circuits, we can say that this situation here can correspond to the case of having a circuit with three elements in series. And each of these elements will have a different thermal resistance R. Well, depending on the geometry of these elements, R will be different as we defined in previous videos, right? So we discuss three different cases. One when we have a flat slab, second one we have a cylinder, and third one we have a sphere. So if we have a case like this, when we have three elements in series, we just need to know the value of the thermal resistance for each of these elements. And then we use the similarities with the electrical circuit to solve this problem of heat transfer. So I mentioned that Q will play the role of the intensity. So Q will be equal to delta T divided by the thermal resistance, okay? And we can play around with this equation. In this case here, we have the delta T defined as the initial point and the final point. But if we want, we can also calculate T3. And in this case, Q will be equal to T1 minus T3 divided by thermal resistance A and thermal resistance B. We wouldn't have to include the third element because we are going to stop in T3, okay? And the heat will be exactly the same. So if I summarize what I say, we can say that this is equal to T1 minus T3 divided by thermal resistance A plus thermal resistance B. And this is equal to T1 minus T2 divided by, here it is, thermal resistance A. Okay? Well, let's imagine that we have a different geometry, different elements, three different elements in series here as well, this one, and this one. But in this case, instead of flat slab, we'll have cylinders. We're going to do exactly the same, but the thermal resistance will be defined as or corresponding to a cylinder instead of a slab, a flat slab, okay? But again, we're going to do exactly the same. What happens if we have elements in parallel, like in this case? We have two different elements, but it's in parallel, so we have two different Qs, QA and QB for each of the elements, and the total heat Q will be the sum of QA plus QB. So the electrical circuit equivalence will be, So the total Q will be equal to QA and QB. And we will have to use the same equations that we will use in electrical circuits. When we have two resistances in parallel, we don't sum directly the thermal resistances, but it's the inverse of the thermal resistances. Okay? And what happens if we have a combination of both? Well, we will have a circuit like this, an electrical circuit like this. What we're going to do is solve first this one in parallel, and that will be in series with the third one. So if we solve this, as I mentioned, we're going to first find the equivalence, the thermal resistance equivalence for the first circuit that is in parallel, and then we use the equation of these in series with the third resistance R3. I think it's probably better if we do an example. So a couple of examples actually, so you'll see how we can solve these kind of situations. So I would like you to try to solve this example with a computer chip, and also this second example when we have a regular panel with two isothermal plates, and try to solve it. I'm gonna solve it in the next video, but I would like you to try to solve it first. I think it's better if you try to solve the problem first, and then you will confirm or you will take a look if you have any questions in the videos with the solution. Okay, thank you.